So let's take a look at this 4-resistor complex circuit. If you can see here that R1 and R2 are wired in parallel with each other, because there's a junction right there where current can split. And R3 and R4 are also wired in parallel with each other, because right there is where the current can split. When the current comes out, it flows this way, and it can split. And when it splits, it'll come together here on this side of this smaller circuit. It'll combine again, and then it'll travel forward. When it hits this junction, it'll split yet again. It'll rejoin on this side of this smaller circuit, and then make its way back around to the source of power. So I know that R1 and R2 are in parallel with each other, R3 and R4 are in parallel with each other, but then resistor 1, 2 is in series with resistor 3, 4. So when I combine these, I'm going to combine these resistors, I'm going to redraw the circuit, and you'll see what I mean. So I'm going to combine R1 and R2 together and get a resistor R12. Looks like that. And I'm also going to combine R3 and R4 together and get a resistor which I'll call R34. And R12 and R34 are in series with each other. 1000 volts. Are in series with each other. So when I combine R12 and R34 together to make a single resistor, which I call the equivalent resistance, because I finally get down to one resistor, which I call REQ, which is my equivalent resistance, and that resistor is attached to 1000 volts. That's a Q. And that's how this particular circuit is wired. So I've combined my circuit down. Now I want to figure out what the equivalent resistance is and then work my way back up and figure out what the values of the voltage and the current through R1, through R2, through R3, and through R4 are. All right? So I'm going to work my way back up. But before I work my way back up, let's start combining some of these things. So the value of R1 is 100 volts. The value of R2 is 250 volts. The value of R3 is 350 volts. And the value of R4 is 200 volts. So I'm going to combine R1 and R2 together. R1, 2. And that's in parallel. So it's R12 to the negative 1 is equal to R1 to the negative 1 plus R2 to the negative 1. And I can do the same thing at the same time. R34 to the negative 1 is equal to R3 to the negative 1 plus R4 to the negative 1. Remember, circuits in parallel, it's an inverse addition. So R1 is 100 to the negative 1 plus R2, which is 250 to the negative 1. And I will make sure to inverse that back. (100 to the negative 1 plus 250 to the negative 1). Inverse that back. And I get an R12 value of about 71.43 ohms. And I'm going to do the same thing here. R3 is 350. It's an inverse addition because it's in parallel. So 350 to the negative 1 plus 200 to the negative 1. Don't forget to inverse your answer back. And I get an R34 of about 127.27 ohms. All right, so that's the value of R12, and that's the value of R34. Now I'm going to combine R12 and R34 together to get REQ. R12 and R34 are in series, which means that these add together directly. So my REQ is R12 plus R34, 71.43 plus 127.27. And I get an REQ of 198.7-ish ohms. So that's the value of my equivalent resistance, is 198.7 ohms. Now I have to figure out what is the total current coming out of this battery that supplies this entire circuit as a whole. So total current, I total, is equal to total voltage, V total, divided by the equivalent resistance. So 1,000 divided by 198.7 gives me, oops, I forgot a zero, 1,000 divided by 198.7. That's better. I get about 5.03 amps. So 5.03 amps come out. 5.03 amps come out here, and 5.03 amps go through R34 and R12. 5.03 amps come out here. At this point, the 5.03 amps will split. Part go to R4, part go, the other half goes, or the rest of it goes to R3. It comes back together, and then it'll split again. Part of it going to R2, the rest of it going to R1. And then when it comes out of this circuit, it goes back to 5.03 amps. So that's what's going on in this circuit here. Okay, so I've worked my way down. I'm going to work my way back up, and it looks like I don't have any room on this page, so I'm going to slide it over and work on this other side. Okay, and I'm going to slide back and forth. Sorry, I wrote too big, or I wrote a lot on a page. So I'm going to go back up. So let's go back up to this drawing here, and we're going to figure out the information for R12 and R34. What is the voltage and the current through R12 and R34? All right. So when I open REQ up into R12 and R34, I open it up in series. And current stays the same in series. So I know that the current through R12 and the current through R34 is the same as the current it was down here. So 5.03 amps. This is 5.03 amps. So 5.03 go here and 5.03 go there. So I know the current through 1,2 is 5.03 amps. And I know the current through 3,4 is 5.03 amps. So there we go. So now that I know that 5.03 amps goes through here and 5.03 amps go through here, how much voltage is consumed by R34 and how much is consumed by 1,2? It is not an even split, and the reason why it's not an even split is because the values of the resistance values of R12 and the resistance values of R34 are not the same. So it's not an even split. So the best thing to do is to use Ohm's law. So I'm going to use Ohm's law here. And I'm going to say the voltage consumed by 1,2 is the current through 1,2 times the resistance 1,2. So that's 5.03 times the resistance of 1,2, which is 71.43, gives me the voltage consumed by R12. 5.03 times 71.43 gives me 359.29 volts. Okay, so now we can do simple math here to get the information of 3,4, or we can use Ohm's law. If 1,000 volts is supplied to this circuit and 359.29 volts go here, then the rest must go there. So I can subtract 359.29 from 1,000 to get the value of R34, or I can use Ohm's law. Let's just use Ohm's law. So the voltage through 3,4 is the current through 3,4 times the resistance of 3,4. That is 5.03 times the value of resistor 3,4 is 127.27. 127.27. And that's 640.17-ish volts. And when I add these two up together, I should get something close. And of course, that's dependent on rounding. So let's just check. I'm going to add 359.29. And I do. I get pretty close to 1,000, give or take some rounding. So now that I know the voltage consumed by 1,2, and I know the current through 1,2, I can open R12 up into resistor 1. I can go back one step and resistor 2. And since I know the voltage consumed by R34 and the current through R34, I can open R34 into resistor 3 and resistor 4. So let's do resistor 1 and resistor 2 first. So I'm going to get R1 and I'm going to get R2. So when I open resistor R1 up, or R12 up, into resistor 1 and resistor 2, I go from a single resistor to parallel, 2 in parallel. And what stays the same in parallel is the voltage. So whatever the voltage was across R12, the same voltage goes across R2, and the same voltage goes across R1, which is 359.29. So I know the voltage here is 359.29, and I know the voltage here is 359.29. I'm going to go R3 and R4. Same thing. When I open up R34 into R3 and R4, I go from a single resistor to 2 in parallel. And what stays the same in parallel is voltage. So whatever the voltage was here, it's the same here. And the voltage through R34 is 640.17 volts. So the voltage across R3 is 640.17 volts. And the voltage across R4 is 640.17 volts, all right? So again, when you open up, when you go backwards and you open up combined resistors into single resistors, you just have to keep in mind what changes and what stays the same, because you already know one of the values from the step prior. Now the current through all of these is based on Ohm's law. So the current through 1 is the voltage across 1 divided by the resistance of 1. 359.29 divided by the value of R1, and the value of R1 is 100 ohms. So I'm going to divide that by 100. And I can just move some decimals, or we can use a calculator. We can move the decimal 2 places, and when we move the decimal 2 places, you get 3.59.3, and again, I am rounding. So I know the voltage across R1 and I know the current through R1. All right, so let's go back up here. So if 503 amps go in and 3.593, I'm sorry, that point shouldn't be there. 3.50, there we go, we'll just hook that 3 there. And 3.593 amps go to R1, that means the rest must go to R2. So we can subtract 3.593 from this number, or we can use Ohm's law. Why don't we use Ohm's law? The voltage or current through 2 is the voltage across 2 divided by the resistance of 2. 359.29 divided by the value of resistor 2, and the value of resistor 2 is 250 ohms. And when I divide 3.59, 359.29 divided by 250, I get 1.437, give or take some rounding. And I'm just going to check that. And I do. I get 5.03 when I combine these two numbers. So that makes sense. I know the voltage across 2, and I know the current through 2. So right here, I know that 3.593 amps go through R1, and I know that 1.437 amps go through R2. And when I add them all up together, it comes back to 5.3 amps when it comes out. So that makes sense. I'm going to do the same thing for R3 and R4. So the current through 3, voltage across 3 divided by the resistance of 3. So 640.17 divided by the value of resistor 3, and the value of resistor 3 is 350 ohms. So 640.17 divided by 350, and that gives me 1.829 amps. Sorry, that should be an amp, not an ohm. So if 1.829 amps go through 3 and 5.3 amps go in, that means the rest should go through R4. And I could subtract, or I can use Ohm's law. And I'm going to use Ohm's law. R through 4, the voltage across 4 divided by R4, 640.17 divided by the value of R4, and the value of R4 is 200 ohms. So I'm going to divide that by 200, and I can divide by 2 and move the decimal. Or you can use your calculator. So I'm actually using the calculator. 640.17 divided by 200 gives me 3.201. Why don't we just go ahead and round it? 2.01 amps. And I'm going to add that just to check. 1.829. And I get 503 amps, or sorry, 5.03 amps. I don't know why I keep saying 503. So that makes sense. 5.03 amps go in here, and through R3, I get 1.829 amps up through R3, and I get 3.201 amps down through R4. And when they combine together, they combine back here to 5.03. So it all adds up. There you go. And I did the exact same thing between the 3 ohm resistor and the 4 ohm resistor. You just have to ask yourself, every time you open up a combined resistor into its parts, what stays the same and what changes. Whatever stays the same, list that first and then determine what changes. And that's what I did. With every step, I listed what stays the same and and then I calculated what changes. Here I listed what stays the same and I calculated what changes. And you can add all this stuff up, especially your current. You can add your current up to see if what splits equals the total. You can add your voltage up to see what splits equals the total, so you can check your work. There you go. I did a 3 ohm resistor. I did a 4 ohm resistor. Good luck. And I will see you soon.